Assalamualaikum everyone, this is casting 5, so let's just continue. In casting 5, I'm going to cover solidification and cooling in casting. Solidification of metal is a transformation of molten metal back into the solid state. So solidification differ depending on whether the metal is pure element or an alloy. So let us see the difference between the pure elements and alloy solidification. So pure metal usually solidify at constant temperature. So if you can see from the graph, um, the the graph is quite simple. Is during the pouring temperature. Okay, you pour the molten metal into the cavity. So what happened? This is the pouring temperature. So during this time, it will start to reduce to the melting temperature. So during this process, liquid is cooling, and freezing will start begin when the temperature reach the melting temperature. So during this time, there will be a local solidification time where the freezing begins until the freezing complete. Okay, so this one we call as local solidification time. Then freezing temperature will start to decrease again. Okay, so this one we call as freezing temperature. Okay, so it will start to um, go down until room temperature, which is the until it reach the solid cooling. Okay, so then this temperature from the pouring time until the freezing is called total solidification time. Okay. So after the molten metal is poured into the cavity, usually due to the chilling action of the mold wall, because the wall is cold, so what happened is there will be the skin. There will be a thick skin where the molten metal will start to solidify on the wall area first, because of the different temperature of the molten metal and also the wall temperature. Okay, so this one will create a thick skin to form a shell around the molten metal. So this area will be inside here will be molten metal. Okay, so once this thick skin already formed, this area inside here will start to solidify slowly. Okay, so that's why it create a dendritic growth of microstructure inside here. Okay, so due to that, there will be grain structure of the thick area or near to the wall will be a randomly oriented grain with small grain, while once it start to solidify in the center, there will be large columnar grain in the center part in the dendritic growth inside here. Okay. So for the alloy, the solidification will be a little bit different. So as temperature drop, freezing will begin at the temperature indicated by the liquidus, and it complete when the solidus is reached. So if we can see the phase diagram of the alloy, so during this process, so freezing will begin when this in this area. Okay, so when this is the liquidus state and this is solidus state, so in between here is will be the freezing begin and until the freezing complete. Okay, so then once it's reached the solidus, so then it will be considered as the solid cooling. Okay, so then the time for the total solidification time will start from the pouring temperature until the molten metal reach the solidus state. For the grain of the alloy during the solidification is a little bit different than the pure alloy. The outer part is the same, still the same, where the molten metal will start to solidify first, and then when it start to freezing, then there will be a certain time where there is combination of liquid and and solid metal in one area. So this area will create this new area what we call as mushy zone. So this when this happen, okay, during the solidification, there will be create another grains inside here instead of the small grain and then dendritic growth, and then there will be another apa microstructure in the mushy zone. So this area, this one, this part that segregate between the dendritic and mushy zone is called ingot segregation. Total solidification time, or TTS, equal to the time required for the casting to solidify after the pouring. So TTS depend on size and shape of the casting. So this one is known as the Shvorynov rule. So how do we express the Shvorynov rules? So the equation is TTS equal to Cm V over A with the power of n. Okay, so TTS is the total solidification time, V is the volume of the casting, A is the surface area of the casting, and N is exponent with typical value of 2. So this is the constant, and Cm is the mole constant. So usually in the question, if the question is given to you to calculate the TTS, the Cm is given based on the mole type. Okay, so the value will be given. So how is the mole constant is determined? So this one Cm is determined depends on the mole material, the thermal properties of the casting metal, and also the pouring temperature relative to the melting point. Value of Cm for a given casting operation can be based on experimental data. So usually they are going to perform the experiment first to determine the Cm value from the previous operations. Then after that experiment, they will start doing the calculation, so you'll get the Cm value. So if you're going to use the same mole material, if you're going to use the same metal and pouring rate, pouring temperature and everything, so the Cm value will be the same. If that the other three things that change, like mole material, thermal properties, and pouring temperature is changed, then the Cm value also will start to change. So what Shvorynov rule tell us? So a casting with a higher volume to surface area ratio will cool and solidify more slowly than one with a lower ratio. So let's see the example. For example, okay, so A, if let's say you have this area, okay, so let's say the volume is the same, but the cross-sectional area of this cavity is this one, okay, this one is A, okay, but the volume, let's say 10 cm cube, okay, so B is like this, so cross-sectional area is big, right? And the volume is still the same. So V over A for this one and V over A for this one will be different, right? So let's say this one is 10 cm cube, but A here is like 10 cm squared. But for this one, 10 cm cube over, let's say 30 cm squared. Okay, so meaning that V over A is equal to 1. Like this one is 0.33 something, right? So meaning that if the ratio of the V over A is lower in ratio, so 0.33, this one will start to solidify first. Why? Because the surface area is bigger. So when it's bigger, so the temperature meaning the temperature can reduce faster compared to this one. It solidify slowly compared to the B. Okay, so that's why with the higher value of V over A, so this one the cooling ratio will be slow compared to the the B part. So that's why using this theory, the riser usually is designed following the A. So meaning that you want the V over A for the riser to be bigger, so that we want the riser to cool slower compared to the main cavity. You can try to solve the problem on solidification time like given here. So the cm value already given, v and a you have to calculate. So then you put it inside the equation here, and then you will be able to determine the value. So that's the end of casting 5. Thank you for listening. See you in the next lecture. Assalamualaikum.